let's do some example problems to apply what we have learned about moles and molar masses. In the first example, it says, in a nanotechnology lab, you might have the capability to manipulate individual atoms. The atoms on the left are gallium atoms with a molar mass of 70 grams per mole. So let's put that here. Gallium and molar mass 70 grams per mole. Those on the right are atoms of astatine with a molar mass of 210 grams per mole. So astatine has a symbol of At and molar mass of 210 grams per mole. How many astatine atoms would the pan on the right have to contain for the masses on the two pans to be equal? Okay, so we want the two sides to be equal. So let's see how many atoms of astatine and gallium we have to have. Okay, so first we start with the molar masses given. For the case of gallium, it says that 1 mole weighs 70 grams. Okay, so 1 mole of gallium, which is equal to 6.0221 times 10 to the 23 atoms of gallium, is equal to 70 grams. So these many atoms is 70 grams because that's equal to a mole. Okay, and for the case of astatine, 1 mole of astatine is equal to the same number of atoms, but this time it weighs 210 grams. So we want these two masses to be equal to each other. So for that to happen, we would need to divide this mass of 210 by 3, right? Because that would give us 70 grams. So if we divide the 210, we have to divide also the number of atoms and also the number of moles. So let's divide all of these by 3. So this gives us 0.333 moles of astatine, and the number of atoms is 2.8656 times 10 to the 17th atoms of astatine, and this is 70 grams. Okay, so this many atoms is required to balance, these many atoms of astatine is required to balance these many atoms of gallium. Okay, so to answer the question, to balance the pan or the pans, you will need 6.0221 times 10 to the 23 atoms of gallium and 2.8656 times 10 to the 17 atoms of astatine. Or in other words, you need 3 times as many gallium atoms as astatine atoms. Let's do the next question. The next question says, a molecule of human DNA was found to contain 2.1 times 10 to the 9th atoms of carbon. Calculate the chemical amount in moles of carbon atoms in the molecule of DNA. Okay, so in this case, we're trying to go from atoms of carbon to moles of carbon. And we are given the information that a human DNA has 2.1 times 10 to the 9th atoms of carbon. And then to convert to moles, we have to use the conversion factor that has the Avogadro's number. So for every 1 mole of carbon, we have 6.0221 times 10 to the 23rd atoms of carbon. So we cancel units of atoms of carbon and we're left with units of moles of carbon on the top. So we multiply 2.1 times 10 to the 9th times 1 and we divide it by Avogadro's number. After doing this, we get 3.48716 times 10 to the negative 15 moles of carbon. Notice that we start with two significant figures, so our final answer must have two significant figures. So we look at the first and second digit, and the third one is an 8, so it will round up the 4 in the second digit. So we will get 3.5 times 10 to the negative 15 moles of carbon, and that's our final answer. Let's move on to the next problem. Epsom salts consist of magnesium sulfate heptahydrate. Write its formula. Okay, so the formula of magnesium sulfate is the following. And heptahydrate means that there is 7 moles of water. So all of these is the chemical formula of this compound. For part A, we need to answer how many atoms of oxygen are in 5.15 grams of Epsom salts. Okay, so let's do part A. We're trying to go from mass in grams of this compound to the number of atoms of oxygen. So first we need to know the molar mass of this compound. So to do that, we define 1 mole of this hydrate, magnesium sulfate, heptahydrate, and for this compound there is 1 mole of magnesium, 1 mole of sulfur, and we find these two just by looking at the formula. There is 1 for every 1 mole of compound, we have 1 mole of magnesium, 1 mole of sulfur, and for the case of oxygen we have 4 here, plus this 7 multiplies both the oxygen and the hydrogen. So for the case of oxygen, 7 times 1 oxygen, we have 7 moles of oxygen, plus this 4 makes 11 moles of oxygen. And for the case of hydrogen, we have 7 times 2, a total of 14 moles of hydrogen. Okay, so we multiply each one of these for their respective atomic mass. For the case of magnesium is 24.305 grams per mole. That gives us the same number in grams because moles and moles cancel. And for the sulfur is 32.065 grams per mole. Moles cancel and we're left with the same number in grams. For oxygen is 15.999 grams per mole. Moles cancel and we're left with 175.989 grams. For hydrogen is 1.0008 grams per mole. Moles cancel and we're left with 14.011 grams. So after adding all of these up, we get the following number: 246.37 grams. And this is for every mole of this magnesium sulfate heptahydrate. So I will just put per mole of hydrate. Let's use the molar mass that we just found to calculate the number of atoms of oxygen in 5.15 grams of Epsom salt. So we're trying to find atoms of oxygen, and we start with mass of hydrate, and we need to convert this to moles of hydrate. And then the moles of hydrate we need to convert to moles of oxygen, and these moles of oxygen we convert it to atoms of oxygen, which will get us to our final answer. And to go from one step to the next, we need a conversion factor for each step. Okay, so let's set this up. We start with 5.15 grams of hydrate, and we need to multiply times the conversion factor that will get us to moles of hydrate. So that one is the molar mass that we just found. So for every 1 mole of hydrate, we have 246.37 grams of hydrate. Notice that grams of hydrate cancels out, and we're left with units of mole of hydrate on the top. Then we need to convert to moles of oxygen. So the conversion factor that we use to go from moles of hydrate to moles of oxygen is the one that we used before in the calculation of the molar mass. For every 1 mole of hydrate, we need 11 moles of oxygen, and that is coming from the formula. So in the formula, we have 4 oxygens and then 7 extra oxygens in the hydrate. 7 times 1, 7. That makes a total of 11 moles of oxygen. Okay, so for every 1 mole of hydrate, we have 11 moles of oxygen. And the units of moles of hydrate cancels, and we're left with moles of oxygen on the top. Finally, we need to go from moles of oxygen to atoms of oxygen. So to do that, we just need the Avogadro's number. So for every mole of oxygen, we get 6.0221 times 10 to the 23rd atoms of oxygen. And the units of mole of oxygen cancels out. So we have atoms of oxygen units on the top. And then all is left to do is multiplying 5.15 times 1 times 11 times Avogadro's number, and divide that result by 246.37, and then times 1 times 1, but that is just this number. Okay, so after carrying out all of this algebra, we get 1.38 times 10 to the 23rd atoms of oxygen. And this is our final answer. Notice that we have 3 significant figures because we start with 3 significant figures from the mass. So having found the answer for part A, let's do part B. So we're trying to find how many formula units of this ionic compound are present in 5.15 grams. So we're trying to find formula units, and to do that, we go from mass of hydrate. We need to convert these to moles of hydrate. And then we convert these to number of formula units. So let's set this up. So we start with 5.15 grams of hydrate. And to go to moles of hydrate, we already know that we can use the molar mass of the hydrate. For every 1 mole of hydrate, we have 246.36 0.37 grams of hydrate. So the units of grams of hydrate cancels, and then we're left with moles of hydrate, and we need to go to formula units. So for that, we use again Avogadro's number. So for every 1 mole of hydrate, we have 6.0221 times 10 to the 23rd, and we have, in this case, formula units. So we have formula units in this case because it's an ionic compound. If we had a covalent compound, then we will use molecules. And if we had just an element of the periodic table, we will use number of atoms. So remember that the units here for Avogadro's number is particles, and that's a general term, which changes depending on what compound or atom you're dealing with. Okay, so units of moles of hydrate cancels out, and we're left with units of formula units on the top. So let's carry out this multiplication of 5.15 times Avogadro's number and divided by this 246.37. So after carrying out this algebra, we have 1.26 times 10 to the 22 formula units. And notice that we have 3 significant figures because we started with 3 significant figures. Finally, let's do part C. How many moles of water molecules are in 5.15 grams of Epsom salts? Okay, so for part C, we're trying to go from mass of hydrate to moles of water. Okay, so in this case, we need a conversion factor. So we start with 5.15 grams of hydrate, and then we need a conversion factor that has grams of hydrate on the bottom and moles of H2O on the top. So the way we do this is the following. Remember that we can get ratios of moles of hydrate to moles of different elements that compose the compound from just counting the atoms in the formula. So we can also see that instead of counting the individual elements, we can also count this molecule of water. So for 1 mole of hydrate, we have 7 moles of water molecules. So we have 7 moles of H2O. Then we can replace that 7 moles of H2O in here, 1 mole of hydrate, and rewrite the molar mass of this hydrate as 246.37 grams for every 7 moles of water. So we can also rewrite this as an example like 246.37 grams for every 11 moles of oxygen. We can also rewrite this for every element that we have. So for example, for every 1 mole of sulfur or for every 1 mole of magnesium. But the conversion factor that we're interested in is the one here. So let's write 246.37 grams of hydrate for every 7 moles of water. And then the units of grams of hydrate cancels out, and we're left with units of mole of H2O. So multiplying 5.15 times 7 and dividing it by 246.37, we have the following number of moles: 0.146 moles of H2O, and remember to have 3 significant figures at the end because the initial mass has 3 significant figures.